All right, let's start off tonight. I just want to go over the flame test lab that we did, just so you understand the chemistry and physics of what happened and what you saw and stuff like that. Just for background. This was the one where we were doing emission lines. When you look up at the fluorescent lights, you should have seen something like this. And the color we see from the fluorescent lights, which is basically white, is because we're getting red, green, and blue, RGB. So that's how they design these things. What you did was to take a solution, really, containing some element, and we sprayed it into the fire. Now, when that happens, that particular element, that atom, will undergo electronic transitions. So let's just pretend that this is a generic atom. We know that the electrons live in different levels, and that these levels are quantized. So there's a set distance between each one. When this atom becomes heated like that, an electron from a lower level will jump to an upper level. So here I've shown two of them. The little asterisk means that that's an excited state. The electron has absorbed this energy. Now, this isn't where it lives. It's not happy here. It has too much energy. There are now too many electrons in these outer orbitals. You know, it's just not a good thing. But it absorbed the energy and jumped up. What it's going to do is fall back down to where it's supposed to be. And as it does, it's going to emit the energy that it absorbed as light. The distance that it falls is related to the wavelength of the light. That's how much energy is given off. So in this particular hypothetical atom, this is our the little thing that we saw through our spectroscope. We have two bands corresponding to two separate transitions. Now, the things that we use don't have much resolution. In fact, under high resolution, you can see lots and lots and lots of bands corresponding to lots and lots and lots of transitions. This is called emission spectroscopy, and it's very, very sensitive. You can clearly identify an element simply by its emission spectrum because the electronic structure is unique for every atom. So any questions on how this happens, why we get light, and why it's always in a nice sharp line? It's a sharp line because there are set distances between the orbitals. When it drops, that's when it emits the energy as light. Now, what we did was actually fairly interesting, using little spray bottles. But there's another way to do flame tests that's even more fun, and that's shown on the video here on the next slide. It's a dark room. These are little...
Very dramatic version of the flame test demonstration here. First we have alcohol burning blue, then we have some barium chloride with barium ions burning a yellow, a dirty yellow color. Then we have boron being green, strontium giving us the crimson red color. Next is calcium giving us the orange. Not showing up very well here in the next one, but the red tints inside of that orange there's some impurities there. That is lithium. Next we have sodium giving us a characteristic yellow flame. Then we have copper with its green color. And finally potassium with the purple or lilac shade.
So that's a really neat thing to do. Just line them up all across the desk, and you make it very dark. Put the metal salts on your little dishes and then put a little alcohol on them and set the place on fire. It really is fun. Well, it's kind of, why don't we do that?
Yeah.
I don't know if they really like us to do that here. All right, today we're going to do Chapter 6. Chapter 6 really encompasses two totally different concepts. Okay, totally different. I'm not sure why they're bundled together like this, but they are. We're going to talk about aqueous solutions. Now, we talked in the chapter on the mole concept. We talked about molarity. That's moles per liter. Here we're just going to talk a little bit about the basics of aqueous solutions, why things dissolve, electrolytes, not electrolytes, just like we did in the last lab. Then on a totally different subject, really, we're going to do the gas laws. Gas laws can be a little intimidating because they involve lots of calculations, but they're very simple calculations. So hopefully we can get through these and it won't be too terrible. When we're going to talk about solutions, we have to understand what a marvelous solvent water is. The reason that water, really two reasons, water is such a marvelous solvent. One is the molecular geometry, and the other is the fact that it contains polar covalent bonds. Now, the driving force for polar covalent bonds are simply differences in electronegativity. Electronegativity is the tendency of a particular element to attract electrons towards itself. It's just an inherent tendency. Highest are up here in this corner, fluorine's the highest, and the lowest are down in this corner, francium at 0.7. The effect of this is to take a covalent bond and to move the electrons so they're not shared evenly, but in fact they're oriented towards the most electronegative atom. So this is hydrogen fluoride. Electronegativity is at 2.1 and 4. And this is the electrostatic potential map. Now remember, in an electrostatic potential map, it's colored so that red shows availability of electrons and blue shows electron deficiency. So what this tells us is that the electronegative fluorine is just sucking all the electrons from this covalent bond down to itself. We'll see that this is a very important thing when it comes to acidity. But we'll do that later. Now we show this using a simple dipole. The dipole is just an arrow that's crossed at one end. And we do this, don't have to color it, but we do this such that this is the positive end of our covalent bond, and this guy is the negative. All right, let's go to water. We all know how to do Lewis structures. Go ahead and just jot down the Lewis structure for water, just to remind yourself. It's been a long week.
Isn't it on here?
Okay, it's on there, but you can do it anyway. All right, I'll remember to delete it next time. Oxygen is group 6, so it's going to have 6 valence electrons, and it's going to look like that. Hydrogen is group 1. It will have 1 valence electron. We have 2 of them, and we'll put it next to these unshared electrons. Now we'll convert this to a line bond drawing, and this is our water. Now, if you recall the discussion we had about valence shell, electron repulsion, whatever, we said that a tetrahedron, or something with 4 groups around it, let's go back to our water here. We have 1, 2, 3, 4 things around the oxygen. That means we're going to have tetrahedral geometry. but we only have electrons in these, and these two are actual covalent bonds. So the nomenclature we give to that is bent. The electronic structure is tetrahedral, but the molecular structure is bent. 109-degree angle between them. All right, now why is that important? Well, because hydrogen and oxygen have different electronegativities. Hydrogen is 2.1, oxygen is 3.5. Now what that means is that these covalent bonds here are going to be polarized, just like we saw with HF. The oxygen is going to draw the electrons towards itself. We have two little dipoles, one for each covalent bond, but these combine to make what's called a molecular dipole. In the molecular dipole, we predict that we will have one end of the molecule here that's positive and one end up here that's negative. So if we look at the electrostatic potential map for water, this is what we see. Down here we have a big blue bottom end, and up here we have rich excess electrons. So water is a very polar compound. The fact that water is polar like this, that it has this dipole, is what allows it to dissolve things like ionic compounds. We'll also see that this is the reason that we can have acids and bases in solution. So here's a cute little movie. This is a crystal of sodium chloride. The sodiums are shown as the little silver guys, chlorine as green. What's going to happen is we're going to have waters come in and pluck this off. This is what happens when an ionic solid dissolves. So let's just watch it. You see the waters come in, they gang up, they grab an ion, pull it up in solution, and that just goes on and on and on and on. Until finally you've got the whole crystal dissolved. That's the process of dissolving. But I hope you noticed that the way the water interacted with these ions wasn't random. In fact, if you look at it closely, we're looking at something like this. The sodiums were always surrounded by waters with the oxygen pointing in. The chlorines were surrounded by waters with the hydrogens pointing in. The reason for that is that with the chloride anion, the positive hydrogens, the positive end of this molecule, is stabilizing its charge. For the sodium, we have a positive charge, oxygens point in, that's these guys, then again they stabilize the positive charge. If water was not able to stabilize these charges and disperse the charges, it would not be able to dissolve anything. Here's a nice demonstration of this. This is going to be another exercise in electrostatic potential maps, but this represents the sodium cation. It's blue because blue means positive, doesn't it? And I've surrounded it here with just 3 waters, just 3. In reality, it would be surrounded by more like 8. 8's the magic number. And again, the oxygens are all pointing in. What we can do with the computer is to solve the whole complex and say, what does this whole complex look like as far as electrostatic potential goes? When we do that, it looks like this. Now we still have a little tinge of blue here and there, but The big blue ball that was in the middle here, this guy, is gone. Just these three waters have managed to totally spread out all of this positive charge over all this space. And if we put, again, more waters, put 5 more, so we have 8 we're dealing with, you really can't even tell it's a positive charge. Water is just remarkably efficient. It is the best substance that we know of for dispersing charge. And that's why things dissolve in water. That's why when we say water is essential for life, well, because it is. If water was not able to dissolve things, if it wasn't polar like this, we wouldn't be able to exist.
Those
Let's
slides-
just-
Those slides that we just passed
Yeah.
were not in here.
Oh, no? Oh, maybe I added 3 more. Yeah, I did that today.
Oh, thank you.
Sorry. All right, let's just do some nomenclature so we know what we're talking about here. Something dissolves, it's soluble in the liquid. Solubility is really a ratio. It's a simple ratio. For example, at 25 degrees centigrade, 1 atmosphere, magnesium carbonate has a solubility of 0.53 grams per liter. That means we can put roughly half a gram of magnesium carbonate in 1 liter. That's its solubility. When we have a maximum amount in there, so let's say we had our liter, and we have managed to dissolve 0.53 grams, we would say that solution is saturated. Saturated means it can't hold anymore. Again, just words, solvent, thing doing the dissolving. Solute is the thing being dissolved. So we just make sure you know the words. Now, when I say that the solution is saturated, it is. It's full right up to its solubility limit. But you can actually fool a solution and make it supersaturated. That is, you put more in that's supposed to be there. When you do this, you wind up with a very fragile solution. Again, way too much stuff dissolved in it. And if you do anything to it, the excess stuff comes out. So this is a little flask, and it contains sodium acetate. This is supersaturated. Way more in there than they're supposed to be. What we're going to do is very, very carefully drop a single crystal, just one tiny crystal, sodium acetate, down the tube here, and it's going to land in here. So let's watch what happens. It's kind of cute. There it goes. It's hit. The second it hit, see the crystals growing from this spot? This is all the excess coming out of solution. When this is done, and it just takes a matter of seconds, you're left with a flask that's essentially full of solid. Whatever liquid is in there is now saturated. So it's gone down to saturated from supersaturated. This also gets very hot. Okay, it gets very hot. This is an interesting strategy for storing solar energy. You take a solution of sodium acetate that's supersaturated, you heat it up with sunlight. Okay, so you wind up with this supersaturated solution. Then the sun goes down. You take this, you induce crystallization, and you get all that heat back. It's kind of an interesting technique. When we talk about solubility, there's a very simple rule of thumb, and that is like dissolves like. Polar compounds will dissolve polar compounds. Nonpolar will dissolve nonpolar. Examples. This is alcohol being poured into water. Alcohol has an OH group just like water does, so it is polar. Soluble in all proportions, we call this miscible. This is oil in water. Oil is a very non-polar compound, this olive oil. Very non-polar. Because of that, you plop it into water, it doesn't have a dipole that water can interact with, so it just sits there and globs. Polar compounds, polar solvents would dissolve polar compounds, non-polar, I meant. And over here we have polar and again polar. So like dissolves like. Very simple concept.
Question. Non-polar versus polar, how do you know? which
Well,
one's
what
there?
you have to do is look at your compound itself. In an oil, we only have carbon and hydrogen bonds. Those bonds are not polar, they're not polarized. Because of that, there is no dipole for water to interact with. Here with ethanol,
No,
here,
but which chemicals are considered polar and which are not considered?
well, anything that has, just like, remember we had water as a molecular dipole? You really have to look at each one. So if it has a molecular dipole, it will be polar. If it doesn't, it's a non-polar. But you have to look at each one. Now we did this on the lab, and we talked about electrolytes. Let's just elaborate a little bit more on this. If you recall from what we did, we said that a compound which dissolves in water to form ions will allow that to conduct electric current. And we call that an electrolyte. Something that did not form ions, we said was a non-electrolyte. The little device that we used was something like this. We stuck the leads here into a beaker or a little container of some sort that had either electrolyte or non-electrolyte in it. And depending upon how well it conducted electricity, the LEDs here would glow. These are glowing nicely. Over here we have pretty much dead LEDs. This is not an electrolyte. Bottom line, as far as the difference goes, sodium chloride, for example, dissolves, forms ions. We just saw that. It's an electrolyte. Here's our sodium and chloride in the solution, glowing brightly. Something like glucose, this dissolves in water because these are OH bonds and they're nice and polar. But when it dissolves, it doesn't form ions and therefore does not conduct electricity. So this is the bottom line difference. You get ions or you don't. Any questions? Well, there's one more neat feature that we want to talk about with regard to water. And this comes about because of the polar nature of the compound. In our water molecule, we have a hydrogen here, right? Oxygen up top. If we put another water next to this, they can interact. These dipoles can interact with each other. When they do, we form what's called a hydrogen bond. We have electron donor, and here's our hydrogen. The positive end of this molecule is accepting electrons. But because of the way water looks, we can also do this again over here. Form another one. And we can do another one up top, actually. We can do two up top, to be honest. Here we have going up from the oxygen this way. So all of these are simple hydrogen bonds. One simple water molecule can interact with 4 others, and we can form 4 hydrogen bonds. Now, hydrogen bonds are weak. The energy for the OH bond, that is, how much energy it would take to break it, is roughly 100 kilocalories per mole. For a hydrogen bond, it's about 5 kilocalories per mole. Nonetheless, if we have enough of them, if we have lots of hydrogen bonds, they really add up. Water has a molecular weight of 18. Things that have a very low molecular weight tend to be gases. Water is not a gas because it is very, very highly hydrogen bonded. This is mapping again for a cluster of water. And I just like to point out, look at some of these guys. This oxygen here has really swallowed these adjacent hydrogens, hasn't it? This is a very, very powerful interaction. Water, once again, is the best substance we know at forming hydrogen bonds. Amazing substance. Now, you've probably heard about hydrogen bonds in biology. This is, I believe it's a GC pair. This is a purine, this is a pyrimidine. In this structure, this is an NH, and this is an oxygen. This can form a hydrogen bond across here, like that. Here we have another NH, and we have a nitrogen that can accept a pair of, or can donate a pair of electrons. So we have another hydrogen bond. And down here we have another NH, another oxygen, and a third hydrogen bond. When we say that the DNA bases pair up with each other, they pair up by this very specific hydrogen bond. In a strand, it would look something like this. This is AT. AT can only form 2 hydrogen bonds. Here we have GC, and this is what we saw. We have 3 very nice hydrogen bonds here. The way these things pair up, the way the strands pair, is by matching the hydrogen bonding between the different bases. The reason, frankly, that this works, however, because these things are all dissolved in water, aren't they? The reason that this works is if you look at the real 3D structure of a DNA strand, these are the base pairs that are pairing up with each other, down in here. And they're surrounded by this ribose phosphate backbone. Basically, it squeezes all the water out. And that's why they can hydrogen bond so effectively with each other, because we get rid of the water as we make our double helix. Kind of an interesting concept. Any questions? All right, hydrogen bonding is a very powerful molecular interaction. We're going to talk about gas laws in just a minute, where we have fairly weak interactions. So let's just do interactions in general, just as an overview. I'm using these 2 little spheres here to represent something like a gas, argon, an inert gas, does nothing. And next to it, I have a sodium and a chloride. These are charged, aren't they? You would normally expect that these charged guys would have no interest at all in these totally non-polar atoms or whatever. But what happens is actually kind of interesting. When they 2 get close together, the sodium and the chloride are capable of warping the entire electron cloud. The sodium will pull the electrons towards itself, and the chloride will repel the electrons and attract towards itself there. So things that have charge, or things that are polar, can interact with things that are nonpolar by this basically induced dipole interaction. Now this is actually very important to you, especially if you're a fish, because water is very polar, but oxygen is not. Oxygen is very nonpolar, 2 oxygen atoms, perfect distribution of electrons. Because of that, you would expect oxygen not to dissolve in water. The reason it does is the induced dipole. Again, the oxygen repels the electrons. Over here, we would attract electrons surrounding the water here with oxygen molecules. That's the reason something like oxygen dissolves in water. If it wasn't for that, nothing would happen. The other type of interaction that we're going to talk about later in the class is what's called a dispersion force. Now this is a very, very weak interaction. But again, if you get enough of them, they can be significant. These again are just 2 little nonpolar things. But electron clouds are such that if you put them close enough together, they will spontaneously orient themselves by warping their electron cloud so that we wind up with positive and negative regions. Think about oils and waxes and stuff like that. If you have a short chain oil, it's very nonpolar. It's a liquid. But if you have big, long, honking chains of it, it's a solid. That's a wax. Why is that? Because the bigger it is, the more of these type of interactions you have, and they stick to each other. This is called a van der Waals interaction. Again, it's very important. We'll talk about this later in the course. Any questions? All right, let's move from oxygen dissolving in water to just oxygen itself. This is the gas laws. In the gas laws, we're going to learn calculations based on volume, temperature, pressure, number of moles, stuff like that. Let's start off with just states of matter. So we just review this for a second. We know that we have solids, liquid, and gases. This is water is a vapor, solid, that's ice, and of course water, that's a liquid.
Is that new slides?
Was that not in there?
It's on the recent slide.
It's on an old one. Solids, we know, have defined shapes and volumes. Liquids take the shape of their container. Gases, however, have neither shape nor defined volume. They take on the shape and the volume of their container. Now, we explained this a while ago in what we call the kinetic molecular theory. In the kinetic molecular theory, we said that these attractive forces, the ones like we just saw, the hydrogen bond, the dispersion forces, whatever, that's what holds things together. Here's our lump of magnets. That's a magnetic force. Okay? Generally attractive forces. When we have a solid, we said that the substance itself doesn't have enough energy. We haven't pumped enough energy in to break these attractive forces. So it just sits there, just a lump. When we have a liquid, we've pumped in enough energy that these things can start to slip and slide all around each other. But they can't break them yet. not enough energy. With the gas, we finally put in enough energy that they are just totally dissociated from each other, and there's no interaction at all. Depending upon the amount of energy we put into something, we can convert it from a solid to a liquid to a gas. So that's our basic phase change. That's why we do that. Let's just review one more time. A gas has an indefinite shape. There's so much space in between the particles. You can compress it or you can allow it to expand. The movement of gas particles is very, very, very rapid. And because of that, it's essentially uniform throughout the entire thing. So those are the important things to remember. Now, gas pressure. This is a really interesting little calculation, actually. It's a movie of this calculation. This is a container filled with gas particles. And they are allowed to move randomly until they bump into each other or the walls. The top air floats. But every time a gas particle bumps into it, it transfers a little bit of energy to it and pushes it up. You can see it bouncing up and down randomly, depending on how many actually run into it. In atmosphere as we know it here, just the pressure from gas particles running into things exerts a pressure of 14.7 pounds per square inch. That's a lot. Over every square inch. That's a lot. This is called atmospheric pressure. Now, atmospheric pressure can be measured lots of different ways. This is a classic barometer. We have several of these little things in the lab. They have a sealed coil in that's attached to the little arm, and it will go back and forth depending upon the atmospheric pressure. This is what we use in lab. It's a mercury manometer. You put this in line with something, pull a vacuum and measure a differential. This is an old-fashioned weather barometer. It makes a little line as it goes. And this is probably the oldest. This is a sealed globe, and it's got a liquid in it. Then it's got this arm coming up that's open. Okay? So, the air pressure inside here, inside this globe, can be different than the air pressure outside. If the air pressure outside gets to be low, what this does is it pulls this liquid up and it will squirt out the top eventually. This is the original hurricane warning device, because there weren't always satellites, you know. There really weren't. I grew up in Florida and actually had one of these things. And when you looked at this and the liquid went up, you knew darn well you were in trouble. So, technology is a lot different now. In the lab, we're going to use what's called a mercury barometer. Mercury barometer, we have a column of mercury here. This is an open vessel with more mercury in it. This is closed here. This closed up top. It's open on the bottom. The way you make this, and we used to always make it in lab, it was fun, you would have this little bucket of mercury. You would take your tube, fill it up with mercury, put your thumb over it, stick it down inside the big bucket, and take your thumb off. And what you did, you drop down, pull a vacuum, and this is the height there represents the pressure at that time.
So your finger touches the mercury?
Yeah, we used to do that all the time.
Is that bad?
Yeah. Yeah, that's why I don't let us do it anymore. But it was fun. So what we're doing is we're measuring the height here from the bed of the Mercury all the way up to the top. This is 760 millimeters at sea level. 25 degrees, I'm sorry, 0 degrees centigrade, 760. This is atmospheric pressure. 760 atmospheric pressure. Now, when we talk about that, we can use an abbreviation here, 1 ATM. If it's written that way, 1 atmosphere, 1 ATM, that's an exact number. It's a definition. There's no significant figures. If I said this is 1.05, that's an experimental number. That's 3 significant figures. This is also 760. This is regarded as an exact number also. Millimeters of mercury sometimes are referred to as torr, T-O-R-R. They're the same, it's just a different abbreviation. We can do it PSI like we did on the previous slide, 14.7 pounds per square inch, but we'll never do that. That's English, not that way. So what we're going to do is use atmospheres and millimeters. All right, let's get right to it and talk about the pressure-volume relationship. Now, I'm going to tell you the answer before we do anything here. This is referred to as Boyles Law. What Boyles Law says is if our temperature is constant, and that's important, the volume occupied by a fixed quantity of gas is inversely proportional to the pressure. Now, I'm going to demonstrate that with this little piston. This is sealed up, this is gas on the inside, this is the pressure gauge, this is a little platform you can put something on. Okay? So, we're going to start off with a very small mass. When we did that, nothing happened. Needle didn't move, whatever. That's a very small pressure. However, if we put something heavy on there, we have lots of pressure and our volume has decreased significantly. That's what this means, inversely proportional. The greater the pressure, the smaller the volume. Here's another little video with the same thing. What's going to happen is we're going to just start pushing this down. As we do, the pressure is going to go up. Volume goes down, pressure goes up. Now you'll note that not only is that the case, not only is it inverse, but it's nonlinear, isn't it? Now think about it, it kind of must be nonlinear because you can't ever squeeze it down to 0 volume because the substance itself has a volume, doesn't it? Mathematically, this is what's referred to as a hyperbola. And if you remember your math, if you're given a hyperbola and you're asked to linearize it, what you do is a simple reciprocal plot. So here I've plotted 1 over pressure against volume, and it's nice and linear. Things that are in a straight line are good, because you can do calculations with them. What this straight line tells us is that volume is proportional to 1 over P. I remember we saw this proportion sign before, didn't we? The proportion sign. Little, looks like a Greek alphabet, it's not quite. All all this says is that volume is directly proportional to 1 over P. That's a straight line. When we see a proportion sign like this, remember we can always replace it with an equal sign and a constant. So we can write it this way. Volume is equal to some constant, don't know what it is, multiplied by 1 over P. This is another way of saying that volume is inversely proportional to pressure. More pressure, smaller volume. All right, let's consider our two cases. Over here, we had our feather. Pressure in this, multiplied by its volume, is equal to K. Take this equation, just rearrange it. So bring our P up here. PV is going to be equal to our K. Okay? Over here with our anvil, same gas, same system. So P2, V2 is also going to be equal to K. But because it's the same system exactly, this K and this K are the same. They're the same number. So if P1, V1 is equal to K and P2, V2 is also equal to the same K, they're equal to each other, aren't
Are you getting those numbers from 1 to 2?
This is, we're just defining this as our initial state, state 1, and our final state, state 2. P1, V1, P2, V2. If I ask you what Boyles Law is, Boyles Law is simply P1, V1, P2, V2.
Boyles Law, B-O-Y-L-E-S.
B-O-Y-L-E-S, apostrophe S, something like that. I'll never ask you his name. All right, let's see how we do this. Here we have 12.5 liters of a gas. I tell you that the pressure on this gas is 0.82 atmospheres. Okay? Now I'm going to change that pressure up to 1.32. What's our final volume? This is a classic Boyles Law problem. So what you do is you say, okay, Boyles Law is P1, V1, P2, V2. Now, we know everything except our V2, don't we? We know P1, V1, and we know P2. We're looking for V2. So we'll simply solve this for V2, substitute, and get our number. There's our Boyles Law. To solve this for V2, all we have to do is divide by P2, and we get this. Divide both sides by P2. Disappears here, goes underneath here. Okay? Now, we know what P1 and V1 are up here. We know what P2 is here. So we just substitute. And now your job is simply to take 0.82, multiply it by 12.5, and divide by 1.32. When you do that, atmospheres cancel. We're left only with liters, that's our volume. And it's 7.8. Now think about this. Initially we had 12.5 liters, right? We increased our pressure. What happened to the volume? It went down. Pressure goes up, volume goes down. You're checking my math, that's okay.
You're on that,
I'm just trying to figure out.
you're on that, right?
Huh?
You're on that.
Yeah,
I got 7 points.
we only have two significant figures, so add around, yeah. Let's do another one. Doesn't have to be liters, it can be any measure of volume. We have 150 milliliters. Here's our pressure in 35.3 millimeters of mercury. We're going to change our volume to 50 mils. We start with a volume of 150, we reduce the volume to 50. What happens to the pressure?
We do the same format with this one. It's different numbers. We follow the same format.
Yep.
Different numbers.
Just different numbers, except here we're solving for P2. So it's P1, V1, P2, V2. That's our expression. And we're simply going to solve for P2. To get P2, we have to divide by V2 on both sides.
Is that always the case?
Yeah, that's how you do it. That's full algebra.
Oh, no, you just, depending on what is given to you, right?
Right.
Like the other one, they give you the
The other one we
pressure.
solve for V.
Okay.
Here we're going for P. So we plug our numbers in. P1 is 35.3, V1 is 150, V2 is 50. Our milliliters are going to cancel. Our pressure is only going to be here in millimeters of mercury. So the math, very quickly then. 35.3 multiplied by 150 divided by 50 is 106 millimeters of mercury. Now, what if I asked you how many atmospheres that was? I don't think it's on this slide, but how would you do that? 1 atmosphere is 760, isn't it? So we would simply take 106 and divide it by 760. And that would give us atmospheres. Now, of course, there's a Boyles Law tutorial. Of course there is. Let's look at a couple. We have an initial pressure and volume of 5 atmospheres and 5,000 milliliters. We're going to change our volume to 5.62 liters. And what's our pressure in atmospheres? Well, we have to do one slight conversion in our head, don't we? This is 5,000 milliliters. This is 5.6 liters. So you could either make this 5,620 milliliters multiplied by 1,000 or divide this one. They have to be the same unit, that's all. Simple Boyles Law. So here I've taken V2, this guy, and just made it into milliliters.
So the P's are always the ATMs?
No, they could be millimeters or ATM.
So how would you know, given the question?
Well,
Just
you would just read it. Whatever you're given. You'll be given some unit. All right, so, see, we were given here a pressure of 5 atmospheres. So that means that's how you know you want to use atmospheres.
Oh, because of the way you read it.
Yeah.
First is the pressure and then is the volume.
All right, so here we're missing P2.
I got a question. Is P2 always going to be an atmosphere? Or is an atmosphere always going to be a P2?
It'll be either be atmosphere or millimeters. Pressure will either be atmosphere or millimeters.
That's a pressure two.
Yeah.
Would it ever be, so pressure one would always be an atmosphere? Or would
It
be
will
an
have a
atmosphere?
unit, one atmosphere.
But it will never be a P1 will never be a atmosphere.
All right, so here's our Boyles Law. Again, P2 is P1 divided by, or multiplied by V1 divided by V2. Here's our substitution. And we're at 4.54 atmospheres. All right, here our P1 is in millimeters, so 2350 millimeters. We have 8520 milliliters as our volume. Oh, here we're changing to atmospheres. And what will the pressure be in liters? So we have two simple conversions here. Have to go from milliliters to liters, just divide by 1,000. You could do that, right? And how do you go from millimeters to atmospheres? Divide by 760. Simply divide by 760. Or you can multiply by 760. Doesn't matter. As long as both pressures have the same units. So we could convert this to atmospheres by dividing by 760.
What's 760?
Remember, that's the definition of one atmosphere, 760 millimeters. That's the definition. And again, here we're looking for V2. I converted V1 into liters just to make it easy. Our equations look like this. P1, V1 divided by P2, that's what we want. We do our simple math, and we're left with 3.58 liters. All right. Gas laws get even more interesting now. Remember, Boyles Law said that the temperature had to be constant. Why is that? Because there's a temperature-volume relationship. This is a balloon. What we're going to do is take and pour liquid nitrogen over this balloon. Now, when we do this, the balloon is going to get very, very cold. Let's watch and see what happens. As the temperature drops, the volume of the balloon drops way, way down. Now, as it sits on the tabletop and slowly warms, it goes back up.
That must be when it's cold outside and you bring the balloons out. they
Exactly.
deflate.
Yeah, it deflates. Exactly. It's not as much fun as liquid nitrogen.
Yeah, I know, right?
So what we have just seen here, this is a direct linear relationship. Temperature is increased, the volume increases. Temperature decreases, the volume decreases. This is what's known as Charles's Law. It's a linear relationship between temperature and pressure. Now, balloons are fun to play with, so is liquid nitrogen, but scientists tend to do things a little more rigorously. So we're going to describe an experiment here. What I'm going to do is take various molar amounts of a gas, and I'm going to change its temperature and measure its volume. So that's all we're doing. Start off with 0.25 moles. As we lower the temperature, the volume decreases. And it's nice and linear, just like we expect. Do the same thing with half a mole. Same result, nice and linear. Temperature decreases, volume decreases. Same thing with 0.75 moles. But something strike you about this plot? All of these are like heading for the same spot down here, aren't they? In fact, if you extend them, they all intersect here at minus 273.15. It doesn't matter what gas it is, any gas at all. You do this experiment, you will get straight lines, and they will intersect at minus 273.15. What is that? That is absolute zero. This is defined as zero on the Kelvin scale. Whenever you have a gas and you're messing with the temperature, you have to use the Kelvin scale. Starts at absolute zero and goes up. Now, this is Charles's law. Charles's law simply says that volume is directly proportional to temperature. Volume gets bigger, temperature gets bigger, blah, blah, blah. We can change this into an equal sign and a KT, can't we? And then just like we did with pressure, let's pretend we have two states, an initial state and a final state. I'm going to rearrange this so the constant is separate. Constant is then equal to V over T. Now if we have two states, initial and final, they're both going to have the same constant, and that is Charles's law. P1, V1, P2, V2, that's Boyle. P1 over T1, V2 over T2, that's Charles.
So this one just changes the temperature instead of the pressure.
Yep, you write these on your 3x5 card.
You say what?
Write them on your 3x5 card for the exams, right? Make sure you know those. Now, like I said, the Kelvin scale is what we must use. Almost all the measurements that you'll take in lab, however, will be on a centigrade thermometer. So you have to convert the two. Fortunately, it's very, very easy. Freezing point is 0 centigrade. Boiling point is 100 centigrade. For the Kelvin scale, they simply differ by 273 degrees. Kelvin is always 273 more than centigrade. Yeah. All right, let's just practice a couple. take these centigrade measurements, convert them to Kelvin. Remember, centigrade plus 273 equals Kelvin. Centigrade plus 273 equals Kelvin. So very simply, our first one here is just going to be 1,273. Here we have to start at minus 150, but we're still just adding 273 to it. And if we're at 100 degrees C, like we just saw, this is going to be 373. Typically, we do this with three significant figures. Drop the 0.15, just do the 273. All right, let's take all of this then and do a problem. Our volume is 50 mils. Our final volume is 62. Our initial temperature is 26.4, and we're looking for the final temperature. Again, we know V1, T1, and V2. All we have to do is use Charles's law and do T1. This is Charles's law, right? Go ahead and solve this for our final temperature. So that's T2. Solve it algebraically for T2. Make sure you can do that. When you solve this thing for T2, it should look like that. V2, T1 over V1. Straightforward algebra. Now T1 here is quoted as centigrade, isn't it? So we have to convert that to Kelvin. How do we do that? We add 273. This makes it darn near 300 Kelvin. All right, so let's substitute in all of our numbers. There's our final volume, that's V2, our initial volume, that's V1, and our temperature, initially about 300 Kelvin. Our volume is going to cancel. Only left here with Kelvin. So the only math to do on your calculator is 62.4 times 300 divided by 50. Let's see, we have three significant figures, so let's round this. What is this in terms of centigrade? We have a Kelvin. How would you get back to centigrade? Subtract it. 101 centigrade.
So will it ask us the centigrade or will it ask us the?
Oh, it'll ask you everything. You mean the tutorial?
The tutorial?
Yeah, it'll mix them all up. You know, the object of the tutorials is to make you do all of these stupid conversions all the time, so you get used to it. And speaking of tutorials, let's do one.
So when it says centigrade, you always have to add the 273.
Yep.
You always have to.
Kelvin is always
Okay.
larger. Just remember, Kelvin is larger. All right, here we have initial temperature and volume of 11,000 mils, 106 centigrade. We're gonna change this to 7.66 liters, and we're looking for our final temperature. We either have to convert this to mils or that to liters. Either way, you can do it in your head, it doesn't matter. I took our liters, multiplied it by 1,000, and made mils. And again, we're just looking for T2. So write your expression, V1 over T1, V2 over T2, solve for T2. Plug in your numbers. T2 is V2 T1 over V1. Here's our numbers substituted in. And this is 264K. If we wanted this in centigrade, what would we do? Subtract 273, because Kelvin's always bigger. Yeah,
How do you convert your Celsius to Kelvin?
how do we convert what?
Celsius to Kelvin.
Just that, just add or subtract 273. Centigrade plus 273 is Kelvin. Kelvin minus 273 is centigrade.
Is it 273.15? You have to have
No,
a
no, no,
273?
273 is good.
How do you know when to subtract 273?
Hmm?
How do you know when to subtract 273?
Oh, if you're either going, which way you're going. Remember,
You have a K.
centigrade plus 273 is Kelvin. Just remember that one. You know, write it on your hand or something. Centigrade plus 273 is Kelvin.
And if you want to subtract it, it's how, when it gives you a K, then you subtract it to get to the C. So you just reverse it.
All right, let's go back to this really neat experiment that we did. It showed us absolute zero and all that stuff. You know, you do a nice experiment, you got all these data. It's a shame not to get everything you can out of them, right? How about if we set at one constant temperature and just looked at the effect of adding more moles of gas? So let's leave our temperature constant, plot our volume here as a function of moles. When we do this, we get a linear relationship. It's going to look like this. This is called Avogadro's law. And it really is very, very simple. All it says is, think about it. The more gas you have, the bigger the volume. That makes sense, doesn't it? The really neat thing that Avogadro showed was it didn't matter what gas it is. But the more gas you have, the bigger the volume. All right, so what do we have for our laws? Boyle says volume is proportional to 1 over P. Charles says volume is proportional to T. And Avogadro says that volume is proportional to N. Now, if all of these things, 1 over P, T, and N, are all directly proportional to V, we can combine all those, can't we? We can combine them. And we can say that volume is proportional to NT over P. All we did is take all of these, since they're all going to be equal to volume, we can just simply combine these sides. Now remember, whenever we had a proportion sign, what do? Put in an equal sign and a constant, right? But instead of calling it K, just to be different, I'm going to call it R. And I'm going to give it a name. I'm going to call it the universal gas constant.
You gave it the name or it's?
No, somebody gave it. I'll tell you the name. All right, but you're never going to see it written this way. Why? Because it's always written this way. PV equals nRT. That's very pleasant to say. It even rhymes, sort of. PV equals nRT. This is our universal gas law. Pressure, volume, number of moles, gas constant, and the temperature. If you know any of these guys, you can solve for the other. That's kind of neat, isn't it? Problem is, what's R? But we know R. At least Avogadro told us how to get R. Remember, he said that 1 mole of any gas at 273, 1 atmosphere, had a volume of 22.4 liters. That was 1 mole. So, we know pressure, temperature, and volume. 1 mole, we know our number of moles. If we simply solve for R and plug all these guys in, first thing I hope you notice is that nothing cancels. Nothing cancels, does it? When you do the math, you get the unwieldy number of 0.082057 with a unit of liter atmosphere per mole per Kelvin. Now, on any and every exam, I will give you this number absolutely because I can't remember it either. Okay? This is the value for the universal gas constant. All right, so let's do some neat things with it. What we're going to...
I'm sorry, can you go back real quick to the last line? Okay, thanks. Got it. You can move forward.
Let me swallow. This is PV equals nRT. Now we know what R is, right? If we know everything except, say, temperature, we can solve this equation for temperature and we can figure it out. This is what's called a single state system. If we factor R out of this and say we're going to have a gas at one set of conditions and then change everything and make a new set of conditions, R is still going to be the same. So we can have an initial state and a final state, but they're both equal to R. Therefore, they're equal to each other. So we have 2 universal gas laws. This one, you're dealing with a single state. You're just trying to figure out what the pressure is, or the temperature, or something like that. This one, you're changing everything. And you're trying to figure out what the new volume is, or something like that. Single state and 2 state. Let's, well, this is, I just said this. This is the single state, and this is the 2 state. Okay, let's do a problem. We have 0.05 liters, pressure of 745 millimeters. Here's our temperature in centigrade. We're going to raise the temperature to 404. The volume expands until the pressure is 106. What's the final volume? All right, is this a single state or 2 state? We're changing things, aren't we? So it's 2 states. We're not trying to find an unknown. It's a 2-state problem. So we're going to use our 2-state equation. Now, obviously, we have a pressure in atmospheres and a pressure in millimeters. It both must be the same. Okay? We have a temperature in centigrade, but you know we have to make that Kelvin. What I did here for P1, I simply took 745 and converted it to atmospheres. How did I do that? I divided by 760. 745 divided by 760 is 0.98. Our temperature was centigrade. I added 273 to it to make it Kelvin. So this is this side of the equation. I left N out because N doesn't change. It's the same on both sides, ignore it. On this side, we are given 1.06 atmospheres. We don't know what V2 is, and our final temperature here is 404. So what you have to do here is simply take this lump of the equation, gonna multiply it by 404, and divide it by 106. Now there's a lot of numbers there, but it's not complicated, is it? You just decide what variable you need, and that's V2 here. Make a couple simple changes in units, and then rearrange it. When we do our math, we'll see that atmospheres cancel, Kelvin cancels. We only have liters, so we got it right. And the answer is 0.0624 liters. We have 3 significant figures. I think that works. A lot of numbers, but again, the concept itself is not complicated. Now, yeah,
One more time, how did you get the 0.98 again?
get 0.98.
Yeah.
Well, 1 atmosphere is 760, isn't it? Just remember that. 1 atmosphere is 760. So to convert millimeters into atmospheres, you just divide millimeters by 760. So 745 divided by 760, 0.98. Now there are 2 tutorials on the combined gas laws. One on two-state and one on single-state. This is the one for the two-state. So let's go ahead and just see if we can mess with all these numbers. Here's our pressure in atmospheres. Our final pressure is in millimeters. How do we convert it? Divide by 760, right? Divide this by 760 or multiply this by 760. That's all.
So when it's millimeters, you divide by 760?
Mm-hmm. And that gives you atmospheres. And let's see, our temperature is Kelvin, so that's no problem. We're liters and liters, so that's no problem. So let's see what we've got here. We're looking for T1. P1 is 0.405, so we changed our 1,000 millimeters to 1.35 atmospheres. Divide this by 760, that's all. V2, T2, we know everything here except T1. So you take your basic two-state equation and solve it for T1. And it should be P1 V1 T2 divided by P2 V2. Now, I'll be honest, I can't do that in my head. I have to sit there and move little units around. Yes, I do. But that's what it is. It's just simple algebra, and we've all done that. Now we just plug in our numbers, because we know all the numbers except for T1. Do our math, and we're at 337 Kelvin.
If we get an error, it'll give us that calculation up on top, right?
Yep. That's exactly where all this comes from. All right, this is the single state problem. P equals nRT. Here we know everything except one thing. And we just have to solve for it.
Is that R?
So we know what R is, 0.082, remember?
R is 0.082.
Here we're looking for the pressure. So let's see. We are given a volume of 5.122 liters. Number of moles is 396. We are at 291.9 Kelvin. And we're looking for a pressure in millimeters. Now, when we do this problem, we're going to get a pressure in atmospheres, aren't we? So to get from going from atmospheres to millimeters, what do? Multiply by 760. 1 atmosphere, 760 millimeters. All right, we want our pressure. We know our volume. We know our number of moles. We know our temperature. We're going to solve this for P, and it's nRT over V. Plug in our numbers, and we get 1.86 atmospheres. Quickly tell me how many millimeters that is. .86 multiplied by 760. 1408. I rounded it up to 1410 for 3 significant figures. In reality, on the tutorial, you wouldn't have to do that. It'll take it anyway.
Why did you read it wrong like that?
Well, because we have 3 significant figures.
Well, wouldn't you have 3 significant figures in
Right.
1408?
In number of moles.
And number 1408, what did that be?
No, that's 4.
4?
Yeah, the 0 counts.
So that other 0 doesn't count because it's after. Got it.
One more time. Our pressure, 1559 atmospheres. We're at 8357 milliliters. We have 0.7 moles. What's our temperature? When you do this, the reason I put this one in, remember, this must be in liters.
You multiply it by 1,000.
Yep, and divide by 1,000.
Divide.
All right, so what we know is our pressure is 1559, our volume is 8.357 liters. We have 0.706 moles. Our temperature, we just take PV equals nRT and solve for T. PV over nR, run the numbers, and we're at 225 Kelvin. What would that be in centigrade? Kelvin is always bigger, so you would subtract 273.
So would that be a negative?
Any questions?
Can I go home?
Not until we do all these problems. These are all exam questions.
You say exam question.
Okay, what is Boyles Law? Which of these matches Boyles Law?
Neither.
A most certainly does, doesn't it? P1, V1, P2, V2. But, remember, to get to this, we also had PV was a constant. So that's true too. Okay? If you take this equation and divide both sides by P2 and then V1, what do you get? P1 over P2, V2 over V1. Algebraically, they're the same. All of these are valid for Boyle's Law.
That's a trick question.
Well, it's not a trick. Little tiny
Just
bit
have
about
to know all those details.
All right, Charles's law. Which of these are Charles's law?
So is TV constant too?
Is that what Charles's law was?
So Charles's law was
T1, V1, T2, V2. That sounds way too much like Boyle, doesn't it? Yeah, Boyle was a P, but that's different than Charles. Same thing with B. TV is not a constant.
None of the above. Oh, no.
Is this,
That one.
is this one?
Yeah.
This is the same as this one, isn't it? This is the proper expression for Charles's law.
Right.
V1 over T1, V2, T2. Not this, not any of it. Now, you know, I'll tell you the history of those last two questions.
So you triggered
This is true, this is the history of these last two questions.
Yeah.
Sometimes exams can be difficult, they can be. And I was thinking up a question or two that I figured everybody in the class would get, because it was so simple. And so I put both of those on there. And nobody got either one of them. I think I was talking to a class of 500 people. So I always put these on my exams now.
Oh, I thank you.
All right, we have 450 mils of a gas at 1 atmosphere. We reduce until the pressure is 5 atmosphere. What's our volume? Pressure volume. Whose law is that? That's Boyle. What is it? V1, V1, V2, V2. And we're looking for what? V2. Right?
So the clue word was P, pressure and volume.
Yep.
Okay. To determine the.
So
the right
V2
volume.
is simply going to be P1, V1 divided by P2. So that's 450, 1 atmosphere, and we're at 5 atmospheres for our final. Do our math, and we're down to 90 milliliters. Pressure goes up, the volume goes down. All right, when you're comparing centigrade and Kelvin, which of these statements is correct? One Kelvin is larger than 1 degree centigrade? No. They're exactly the same. Kelvin and Celsius are never numerically equal. They never are equal because Kelvin's always bigger, isn't it?
What were you saying then? So it's B? Yeah, he's tricking us. So your final answer?
Let's see, we're 25 centigrade, 1 atmosphere, when that's 150 mils. 100 degrees centigrade, 1 atmosphere. The gas sample will occupy what? This is temperature volume, right? Temperature volume, so this is Charles. So step 1, what's Charles' law? V1 over T1, V2 over T2. What are we looking for? We're looking for our final volume. That's V2. So we simply plug in. Whoops, we don't do that yet, do we? Because this is both centigrade. So what do? We add 273 to both of them. This gives us 373 and 298.
You add 273 to the 100?
To the 25 and the 100, because they're both centigrade.
Oh, okay.
They
'Cause you have to
all
convert.
have to be Kelvin. Multiply and divide. We're at 1.88 liters. If you think about it, we are raising our temperature from 25 to 100, and the volume goes up from 1.5 to 1.8.
I get 298.
298, 25 plus 273. All right, this one you have to do 2 things. We're looking for a mass of argon. We know a volume, we know a temperature, and we know a pressure. This is a single state problem, isn't it? Except we can't get a mass, we could get a number of moles. So what we're going to do here is solve for the number of moles. Then we're going to look at the periodic table and see what the mass of 1 mole is. This is PV equals nRT. We're solving for N, the number of moles. Let's see, you have to take our 20 and add 273 to it, right? And everything else is okay. So our number of moles, that's in here, it's going to be PV divided by RT. PV RT. So we run those numbers and we get 1.81 moles. Now, we look at our periodic table, if we can see it. Argon looks like it's about 39.9 grams per mole. We have 1.8 moles, simply multiply it by 1.8. And we have 72 grams.
Where did you get that -1 from?
That's just another way to write the units, remember? this means liter atmosphere per mole per Kelvin. You can make a slash and put them underneath, or you can just put minus ones. Minus one makes it easier on a word processor. All right, last one.
What was the answer to
Last one. We have 35 liters of methane at STP. What's STP? When I was a child, it was a motor oil additive. STP is standard temperature and pressure. Standard temperature and pressure. At standard temperature and pressure, that's, everything is defined as sea level. Sea level, 0 degrees. All right. We have 35 liters of methane. How many moles is that? Now we could do this the hard way. We could do PV equals nRT, couldn't we? We could do that. Or you could just think about Avogadro and his cute little face. 1 mole occupies what volume? What's his magic volume? 22.4 liters. Doesn't matter what gas it is. 1 mole, 22.4 liters. So, 22.4. So if we have 35, and every mole is 22.4, we simply divide 35 by 22.4, and we get 1.56 moles, which unfortunately doesn't match anything, but. All right, I know this is a little bit of a challenging chapter, but we got some nice tutorials out of it. We have Boyles, Charles, and I think there are 2 combined gas law tutorials. I think I made a mistake when I did that. I think there were 2. So 20 more points that you can get just on these tutorials. Now, once again, I'm going to say the magic words here. We have, I think, 1 more chapter that's fairly math intensive, about like this, then straight slope downhill. Then it's just nothing but fun. Earth science, radioactivity, good stuff. Yeah.
When we left for break, we went over, I believe it was chapter 5 on some type of exponential notation. But it was like the advanced exponential notation. Is there anything that you can give us that had to do with the actual
The best one is to go back to the very first tutorial on the page, X-Roads.
Well, no, not